All right, we're going to start with radioactive dating. This is part of the larger lesson on geologic time and how geologists think about time. If you're enjoying this or you wish to know more or go in depth, we have a couple different options on how to do this. First of all, this is all going to be corresponding to Chapter 8 in your text. And this first lecture is going to be corresponding to what you read on pages 207 through 209. So, determining geologic time is not going to happen if you just call up Brian Butterfield like the people are doing in the first video. Geologic time is going to be determined by one of four methods. The first, there's no particular order to these. Each has their benefits and pitfalls, but when used in conjunction with one another, you can get a very powerful tool for determining the ages of many geologic units. So the first one, see this up here on your screen, is using radiometric dating to determine the age of a sample. So to understand how this works, you first need to understand a little bit more about the concept of isotopes. This takes us back to the atom, which we learned about during the "And the Crazy Cat Lady" lecture. We talked about how an atom has protons, neutrons, and electrons, and that the protons have a mass of 1, a charge of 1. Neutrons have no charge, but a mass. Electrons have a negative charge and a very, very tiny mass. What we didn't tell you about was the fact that we have the number of neutrons can vary and the element stays the same. So whereas switching out, adding or subtracting protons turns your atom into an atom of different elements, adding or subtracting neutrons does not change a thing about your atom except its mass. So a hydrogen atom with an extra proton is still hydrogen. So likewise, the atom on the left side and right side of the screen are essentially the atoms of the same element, except that one has a couple more neutrons, making it heavy. And so the term we have for atoms with the same number of protons, but differing numbers of neutrons, we call them isotopes. And isotopes come in all flavors, both stable and unstable. So if you looked at your periodic table, you probably noticed on the atomic masses, which are not evident on this version of the periodic table, that many elements, their atomic mass was not a whole number. The reason that the atomic mass was not a whole number was that atomic mass was an average atomic mass. And if you have a large enough sample of that element, you're going to have differing isotopes, and the average mass of all those isotopes is your atomic mass that you see on the periodic table. So, just because an atom happens to have 1 or 2 extra neutrons or 1 or 2 fewer neutrons does not make it necessarily radioactive on time scales relevant to anything we're going to care about. It's only when that nucleus has enough is unstable that we can start to use it as an atomic clock. Now we're going to turn to the concept of Schrodinger's cat. This is a nice sort of metaphor for how we understand radioactive decay and atomic nuclei. And a little bit about why it is that you'll understand terms like half-life and other things like that. So, the basic premise of Schrodinger's cat, feel free to look this up on Wikipedia if you get a little confused on it. It's sort of we're sort of venturing in the realm of philosophy. The idea is a cat is placed in a box with a single atom of a radioactive element, unstable isotope, and the isotope has a 50% chance of decaying before the scientist opens the box and rescues the cat. If that isotope decays, it sets off a trigger which poisons the cat. And so the premise is that you don't know if that radioisotope has decayed until you open the box. Another way to think of it is that when you have an unstable isotope of an element, you do not know when a single isotope decays. Regardless of whether its half-life is 1 millisecond or 1 trillion years, you do not know for certain if a single atom of that isotope has decayed until you check. It's sort of a random, unpredictable process. Well, I can't predict the behavior of a single atom. You can predict the behavior of a population of atoms. So, just a little bit more and so, what happens when you have an unstable isotope is that you can see a nice little diagram of it on page 208, is that what will happen is one of those neutrons might decay into a proton. That's what happens when carbon-14, an unstable isotope of carbon, decays into nitrogen-14. In this case, what you're seeing in your textbook is that an electron's emitted and some protons decay. The atom gets a little bit lighter. This is also that whole sort of E equals mc squared thing. Now, it's going to matter to you for your learning experience. Your learning experience using this clock is the diagram that you're looking at on the bottom of this page. And I'll be honest, I actually have some issues with the way this diagram is done. This sort of portrays the radioactive decay process as the unstable isotopes on the bottom of that ball decaying first, and the radioactive isotopes on the top of that sort of cluster of unstable isotopes decaying later. Reality is, if you looked at this, and some textbooks display this better than others, it would actually be a much more random process. And so that first panel and the last panel would definitely be pretty much the same, but these middle panels would look a lot more like a potpourri or a pointless painting. This is probably also where I should introduce the term parent isotope and daughter isotope. So when you have an unstable isotope, your parent isotope is the initial unstable isotope. The daughter isotope is what your parent isotope decays into. And so we like to use the term for radioactive decay, we call it half-life. Half-life, defined, is the amount of time it takes for half of all parent isotopes to decay into daughter isotopes. And the thing is, this half-life can apply for any population, basically, greater than about 30 or so parent isotopes. Now, the length of the half-life is going to vary depending on the isotope. You can see on page 209 of your textbook a list of many different unstable isotopes commonly used in the earth sciences and also in archaeology and anthropology, all of which are used to measure different intervals of time. So, for example, what we have here up on our screen is uranium decaying into lead, and the half-life of this is about 700 million years. So, if you start off with a pure sample of parent isotope, this is actually fairly rare, but we're going to keep the model simple for everyone. After a single half-life, in this case 700 million years, half of all those parent isotopes have decayed into daughter isotopes. So then after 2 half-lives, this is the common misconception. A lot of people would say, oh, after 2 half-lives, that should be enough for everything to decay. But no, remember, at any interval time, that half-life is the amount of time for half of all the parent present. So, in this case, if you start off with 1 million parent isotopes, after one half-life you have 500,000 parent isotopes. And so your half-life, after another half-life, half of all those will decay and you have only 250,000 parent isotopes. So in your book, you have this really nice relationship from decay, and you usually on the exam ask a couple questions about talking about parent isotope and daughter isotope. And this graph on the bottom of page 208 really does a nice job sort of helping to figure out how, for a given number of half-lives elapsed, how many parent isotopes and how many daughter isotopes. And so what typically happens after about maybe 6 to 10 half-lives, depending on how much parent isotopes you have present, is that the amount of parent isotope never disappears completely, but it gets to be so small that it falls below detection.